Hello everyone, welcome to today's deep dive into two classic sorting algorithms, insertion sort and selection sort. In this session, we'll take a closer look at the inner workings of each algorithm through detailed code explanations. Later on, we'll put them to the test with a performance comparison using a random dataset. Let's jump right into it. Let's begin our exploration with the insertion sort algorithm. This algorithm operates on the principle of gradually building a sorted array. It starts with the assumption that the first element is inherently sorted and then iterates through the remaining unsorted elements. At each step, the algorithm compares the current element with the elements in the sorted portion and inserts it into its correct position. Let's visualize this process using an example. So, the input array in this program is 12, 11, 13, 5, and 6. So obviously it is unsorted. Let's try to run this program. So the original array is 12, 11, 13, 5, and 6. Then the program sorted it to a new set which follows 5, 6, 11, 12, and 15. As we can see, the insertion sort algorithm efficiently builds a sorted array by iteratively inserting each element into its correct position. This makes it particularly effective for smaller datasets and partially sorted arrays due to its simplicity and adaptability. Now, let's shift our focus to the selection sort algorithm. This sorting technique works by selecting the minimum element from the unsorted portion of the array and swapping it with the first element of the unsorted portion. This process is repeated until the entire array is sorted. Let's explore this algorithm further using the same example. Now let's try to run this program. Just like in the insertion sort, the original array is 12, 11, 13, 5, and 6. And the, the selection sorting program sorts into a new array which is 5, 6, 11, 12, and 13. Selection sort, although less intuitive than insertion sort, is known for its simplicity and ease of implementation. However, its performance characteristics are worth considering, especially when dealing with larger datasets. With a solid understanding of both insertion sort and selection sort, let's move on to the exciting part, which is comparing their performance. We'll use a random dataset of 1,000 elements and measure the time it takes for each algorithm to sort the data. The comparison will provide insights into their efficiency for the specific dataset. Let's try to run this program. As you can see, the insertion sort time has 0.0291 and so on. Then the selection sort time is 0.01961. Let's try to run this again. It almost displays almost the same results as the previous ones. Let's try as we execute as we execute these algorithms on our dataset, we'll, um, we'll discuss the results and consider factors such as time complexity, adaptability, and suitability for different use cases. After running our tests, we've gathered valuable insights into how insertion sort and selection sort perform in practice. We've observed their execution times, discussed their strengths and weaknesses, and considered factors that might influence the choice between them. Remember, the performance of these algorithms can vary based on data characteristics and the specific requirements of your tasks. In conclusion, both insertion sort and selection sort play essential roles in sorting algorithms, each with unique characteristics. The choice between them depends on the specific context and the nature of the data you're working with. Thank you for joining us on this exploration of insertion sort and selection sort. I hope this deep dive into these sorting algorithms has been informative and helpful. Thanks for watching.